this nice lecture. And because short of time, let's jump to the next speaker is Haba. No? Volt változás? Okay.
Nincs átszás, csak sejtésre.
So our next speaker is Tamás Haba, who is going to speak about GPU acceleration of a simple cell mapping algorithm. I think I remember correctly. Yes.
Thank you very much for the introduction. Welcome everybody. Good afternoon. My name is Tamás Haba. I'm a PhD student at Budapest University of Technology and Economics. And my talk is titled GPU Acceleration of the Simple Cell Mapping Algorithm. Many engineering applications involve mechatronic systems. And when we want to analyze such systems, we might want to consider both the digital effects from controllers and both the nonlinear properties from the controlled physical systems. For example, here is on this picture, you can see an electric drive, which is an electromechanical system. It can have many nonlinear properties, friction phenomena, or actuator, saturation, etc. And these combined effects will make the dynamical analysis really difficult. And one possible approach for dynamical analysis is based on linearization. But linear models are only accurate around an operating point, and this makes only local analysis possible. For global dynamical analysis, we have some numerical methods to use, but they can have high computational costs, and this is why this research aimed to utilize parallel computing to solve this problem. So what exactly is a dynamical system? A classical dynamical system can be described by an n-dimensional ordinary differential equation, where we have an n-dimensional phase space or state space, where every point in the space corresponds to a state of the system, and it can be characterized by a flow map, which is a function that tells us what happens to an initial state after a given amount of time passes. And the goal of the dynamical analysis, global dynamical analysis, is to find equilibrium points, periodic orbits, or bifurcations of this system. And a very common numerical approach to do this is called cell mapping, or it's a family of numerical methods. And they are basically discretization, both in space and time, of the system. And instead of the phase space, the analysis is carried out on a so-called cell state space, which is a finite discretization of the phase space. And instead of the flow map, we have a cell-to-cell mapping. And using this cell-to-cell mapping, we can iterate this function and build cell sequences. And the goal is to solve a cell mapping. And by solving a cell mapping, I mean, we want to find periodic solutions and transient cells leading to the periodic solutions. And another goal is to identify the different periodic groups, and there are a handful of algorithms to identify each periodic group and each cell type, so whether it can be periodic or transient cells. The most so basically the simplest algorithm is the single cell mapping, or the SCM algorithm. And the cell structure, or the cell representation, consists of a cell identifier, a group identifier, which identifies the periodic group, a cell type, which can be periodic or transient, and the cell state to keep track the progress of the solution. And the simple cell mapping algorithm works as follows. So we start by choosing an unsolved cell and build a cell sequence from that. And along the solution, for each cell, we check its state. If it's unsolved, then we mark it under processing, and we go on until eventually we end up on an already marked cell. In this case, we are sure that we found a new periodic solution, so that we assign a group identifier to all these cells and assign the appropriate type. So these 3 cells will be periodic, and these 2 first cells will be transient cells. We repeat this process and find another unsolved cell and start all over again. And it is possible that we reach an already solved segment. And in this case, we just append the newly found cells to the existing periodic group. We do this until there are no more unsolved cells in the cell state space, and that's when we are done. So it's a pretty simple and intuitive algorithm to classify the cells and the different periodic groups. And the main idea here was to speed up the cell mapping algorithm by using parallel computing. And the idea is to start from separate cells with separate solver threads. And this raises some challenges, because it is possible that race conditions occur when 2 cell sequences merge at a common point. There's problems regarding memory access and performance, because it's not ideal that 2 threads calculate the same trajectory. And another huge issue can be when the 2 working threads are exploring the same periodic orbit, because there might be an issue with assigning an identifier to that periodic group, because one thread might want to assign the group identifier 1, and the other thread might want to choose the identifier 2 for that very same periodic group. That can cause conflicts. So in this work, in order to parallelize the SCM algorithm, both the algorithm itself and the cell representation had to be changed. These are the main changes in the cell representation. We got rid of the cell identifier, because all cells are basically stored in a big array, and the cell indices can also identify the cells, so there's no need to store them separately. And instead of the threads owning copies of the cell state spaces, they share the same array of cells. And only the solution states are stored thread by thread. All of the other variables are shared across the threads. And for the group ID problem, group IDs are assigned based on the smallest cell index in a periodic solution. So that basically is a canonical way to assign group identifiers. So matter which thread finds a specific periodic solution, they will always assign a unique and well-defined identifier to a periodic solution. The parallel cell mapping algorithm has been implemented in OpenCL, and here are some key details of the implementation. All of the cells, so this big cell array, the cell state space, is stored in global memory. And each work item will start from a different starting point in the cell state space, and they will scan through the whole state space to find starting points to build cell sequences. And there are some synchronization calls in order work items to wait for each other to finish the memory operations. And the implementation is tested on the so-called microchaos map, which is basically a state space model with a state feedback controller. And this state feedback control has a truncation also. And here you can see the parameters of the cell mapping. And this is a solution of the cell mapping on a 1920 by 1080 sized cell state space, where different colors correspond to different periodic groups. You can see that this system has very rich dynamics, so it's a very good candidate to test these this kind of global dynamical analysis tools on. And it has many equilibrium points, even some chaotic attractors. But the most important question is that how does it scale? So as you can see on this chart, when we start to increase the number of work items, we can see an improvement in the execution time. But eventually, it will reach a plateau, and after some more number of threads, this weird staircase form characteristics will be provided. So it's far from ideal. So what could be the problem here? What can we improve, and why are these staircase shaped characteristics present? Okay, so a huge problem could be memory access because global memory is the slowest to access, and the whole cell state space is stored in the global memory. But at first, this is not a trivial problem to solve, because the cell state space is so big that we cannot store that locally. And another problem is that as the trajectories of the dynamical system spread across, it will cause random memory access. So this means another huge performance penalty. But another key problem is thread divergence, because in the initial implementation, the work items are assigned to the same compute unit in the same work group, and that means that they share the same program counter. In this scenario, at every given point in time, all work items execute the same operation, the same instruction, and when there are branches and the different work items try to execute different branches of this if statement, they have to wait for each other to finish, and that's a huge performance penalty. So they will block each other from executing, and this is why we see those plateaus in the scaling diagram. And here's a possible solution. Let's just assign each work item to a separate compute unit and see what happens. at first glance, you can see that that the improved approach made the algorithm much more scalable, and we can explain why we saw these staircases in the initial implementation. So it happens to be the case that on this platform, on a compute unit can execute 32 work items, and when the number of work items equals to 32, this is when they are blocking each other the most. And when there's another one, so when we are having 33 work items, the 33rd will be assigned to a completely new compute unit, which will not be affected by the other threads. But when we deliberately assign each work item to a different compute unit, we can get rid of the problem. Okay, so in conclusion, this work aimed to examine the application of parallel computing in the analysis of mechatronic systems, and the goal here was to make global dynamical analysis. For this purpose, we parallelized the simple cell mapping algorithm, and we also implemented that algorithm in OpenCL and tested it on GPU. And the execution tests were carried out on a micro-chaos map. So thank you very much for your attention, and feel free to ask any questions.
Thank you very much for this nice presentation. Is there any question? Then, and what are the with this algorithm?
So basically, these are just preliminary results, and I think I haven't found GPU implementation of the cell mapping algorithm. So this work was basically a proof of concept. But because of the huge thread divergence problems, maybe